Hello and welcome to Lesson 23. Today's topic, we're looking at geometric distribution. So what's today's goal? At the end of this, I can identify the appropriate time to use and successfully apply geometric distributions. So by the time the lesson's done and the homework is complete, that is your goal. So let's talk about geometric distributions. So the geometric distribution, slightly different than the previous two concepts we talked about, uniform distribution and binomial. Often this is how companies that are manufacturing parts determine how long it is until they experience a failure. So it's what we're looking for is how long we have to wait. So we're looking at a length of time and we're looking at waiting period until a product or an item fails, okay? Or the flip side, or we have a success. So it depends on the situation. So geometric distribution, the focus is on waiting times. That is the main thing with geometric distribution. We're worried or concerned with waiting times. So very, very similar to a binomial distribution. The following has to be true. You have to have identical trials. There has to be two outcomes. And the probability of success for each trial must be the same. And the trials are independent of each other. That means that whatever happened the first time doesn't affect the outcome on the second. So those are the four things. So it's exact same as binomial in terms of your requirements. Okay. The difference is now that we are seeing how many successes, so how many times will we be successful before a failure occurs. So the focus again, and I can't stress this enough, it's our waiting times, okay? We're really focused on waiting times. So let's move along. All right, so an example to illustrate. So determine the probability distribution for rolling doubles with two dice. All right, so if we create our distribution table here, very, very similar. This is our small x, and this is the probability of that event occurring, so a random variable. The thing you need to remember in that x column, it is waiting times. Okay? So what happens if I roll doubles on my first roll? So if I roll the dice and I get 2 2s or 2 4s, I had to wait 0 times. What's the probability of this happening? Well, there are 6 possible doubles out of 36. So 6 36ths, or 1/6. What happens if I roll doubles on the second roll? That means that I didn't get it on the first, so I had to wait 1 roll. Now, I failed on the first attempt, which means that it was a 30 and 36 chance of failing, but I was successful on my second roll. So now, that's the probability, or my waiting time. So if you can convert some of these into decimals for you, so 0.17 or 17% chance. Now the second one, 6 and 30 and over 36 times 6. So now it's 5/36 or 0.14 if I wait twice. That means I had 2 failures. So 30 and 36 times on my second roll I failed, and on the third roll I was successful. So I'm just multiplying it by 30 over 36, so 0.11. And that is what we're developing here. If I did it on my fourth roll, that means I waited 3 times. So that means I have 3 failures before having a success. And the chart would continue on. So that's what we're looking at with a geometric distribution. We're seeing how long do I have to wait in order to be successful. 0. That's roughly, let's call that 0.10. Okay, so there is our distribution, and it continues on. It continues on downward. So in B part, predict how many rolls it would take before we get our doubles. So you can see that the probability, as the waiting times increases, if we look down this side here, those probabilities are decreasing. So, and you'll notice that the probability of having to wait that long is decreasing. So you're thinking, in your head, you're thinking, well, why is the probability decreasing as we go here? So it's decreasing, but it's decreasing because it's saying that, well, to wait for your third roll or your fourth roll, you should be getting ahead by then. And if we continue on, it's going to approach 0, because at some point it's going to say you should have rolled doubles by now. So using common sense, because at this point we haven't talked about the formula, how long should I have to wait? Well, it should say in 36 rolls, you would assume that you would get 6 doubles, because everyone should appear. They all have an equal chance of happening. Sorry, that's not true. Every outcome of those 36 has an equal chance of it happening. So if 36 rolls, it's 6 doubles. If I reduce it, 6 rolls should produce 1 double. So this is just using straight logic. I'm going to provide a formula in a second. So therefore, we should have to make 6 rolls, or, and this is the big part for geometric, wait 5 times. So if you wait 5 times, you had success on the 6th roll. Okay? So formula. When you are coming up with the formula here for our distribution, probability looks like this. Same notation that we've moved to now with distributions. And in this case, we are looking at our probability of failure. And remember, that's a relative term multiplied by our success. So if you look above, that's what was developing up here. Okay? So we had a failure multiplied by a failure, multiplied by a failure, multiplied by success. So X represents the waiting times. Okay? So underneath, where X is waiting times, Q, probability of failure, and P is your probability of success. All right. Expected value. The same formula exists, so it is your waiting times multiplied by the corresponding probability. However, when you do this, in terms of the dice, if you look at the example we just talked about, you could roll 20 times, 100 times, 1,000,000 times. It could go on forever. So we put the infinity sign above it because it indicates that it's going to go on forever. Now you're thinking, well, how do I add up x times px to infinity when there's no, it's not possible, I don't have the time? That formula, when you do a finite analysis on that, and we don't need to worry about it in this course, it reduces down to Q divided by P. So the actual formula that you will be wanting on your cheat sheet, or your formula sheet, is this one right here. It does come from this one, but in the end, when you do the advanced math analysis on it, that's what it reduces down to. So there are the two formulas that go with geometric distribution. You want to make sure they're on there as well and clearly marked so that you have access to them during a test. All right. So I'm looking at the example here. It says that Olivia has a success rate of 68% for scoring on free throws in a basketball game. Answer the following. Determine the probability Olivia will miss on her fourth shot. So A part. So we are looking at fourth shot. The fourth shot is the equivalent to, so I'll put an arrow here. If I'm looking at the fourth shot, how many times did she make it? So she made 3 shots before that. So I have 3 waiting times before, in this case, failing. So that would mean that our x value is 3. Now, P and Q you have to be a little bit careful with. So in this case, determine the probability that she will miss her fourth shot. So that's a success. Okay? And it says up here that her success rate for scoring is 68%. So on the first 3 shots, it's going to be 0.68, even though it's marked as a failure, because for us, success occurs when she misses. You know, as mean as that sounds, okay, that is what we're looking at. So, probability of missing, okay, so that's what this is right here, missing, which is our success, when will she miss, is 0.32, and this is scoring. So that's the trickiest part right here, those three items, being able to tell me waiting times, being able to tell me success and failure. And remember, the same as it was before in the previous examples, success and failure is a relative term. Relative term means it depends on the situation. We don't care that she can make the basket, it's when will she miss. So the calculation then, we got our Q value. So she is going to be successful, or score I should say, 3 times before finally missing. And if you look back to that example with the dice question, okay, that's what we're doing. Failure, failure, failure. Ha, finally happened. Same thing here. We are looking at, oops, we are looking at, with the 3 in the exponent, made a shot, made a shot, made a shot. Finally she missed. Okay, so that's what we're doing. We're waiting to see when that occurs. So when you do the calculation for that, punching it through the calculator and using the exponent button, so 0.101, which translates to, therefore, there is a 10% chance she will miss her 4th shot. Okay, so 10% chance she misses her 4th shot. B part. Determine the expected waiting time before she misses on a free throw. So if she's at the line, expected value for this particular, for geometric is that. We've already done the tough work, and like I said, this will be the challenging part right here, is identifying P and Q. We've already done that work, we just need to plug it into our equation. So again, 68% chance of failure, and failure for us is her making it. So I guess we're looking at it from the opposing team point of view. And when we calculate that, 0.68 divided by 0.32, so 2.125. Can you have part of a shot? Absolutely not. So therefore, we would expect Olivia to miss after, and here's where it's tricky, after 2 waiting times or on her 3rd shot. Okay, expected is going to come back with waiting time. So we're going to have to wait twice before we expect her to miss, which translates to her 3rd shot. All right, one more example to finish up, and then we're done this particular note. We'll see you in a minute.